Okay, so we're going to continue on here with chapter 4. And so now we're going to go ahead and talk about conditional probability. And let me go ahead and put a little bit of notation here. We're going to call this P of event B given event A. And so what that looks like, it's P of A and B over P of A. And this notation, this slash sign is considered given. So think about the conditional as I'm giving you a hint. I'm going to select someone in class. So I'm thinking of a person in class, but I'm giving you a hint that they're wearing glasses. So you wouldn't worry about everyone else that doesn't have glasses. We're narrowing down that sample space to just a small group that we have there. Okay, so let's make up a little table here. Let's say I did a little survey and I asked people their preference on cola here. So males, female, we got Pepsi, Coke, and RC. And let's just say this many people have for each of them. So we have 15, 18 for Pepsi, 12 and 9 for Coke, and then 2 and 1 for RC. And what's always helpful, as usual, is go ahead and write the totals if they're not given already. And so we'll add, go ahead, horizontal, males and females. And then you want to add everything down vertically as well. And this grand total is always a good idea to actually end up doing it both ways. So both horizontal and vertical to make sure you got that 57 there. Okay. And so let's look at some of this here. Sorry, let me readjust some of these graphs here. Okay. All right, there we go. Okay, so let's do a probability. So what is the probability that I select a person who likes Coke here? So person who likes Coke. But we're going to say that there's a given part to it. So given that they are male. Okay, so what is the probability I select a person who likes Coke given that they are male? So I'm pretty much giving you a hint already. I'm telling you that the people I'm thinking of is going to be a male. So that's going to kind of be the subgroup that I want to think about here. So let's put some notation. It's probability they like Coke given that they're male. And you could use any letters, any notation you want. I try to use the first letter that talks about the event we're talking about here. And let's do it formally first with the formula here. So we're saying that they like Coke and they are male over the probability that they are male. So this is the official formula here. And so let's talk about that numerator, that they like Coke and are male. So let's look at those two groups here, which is going to be 12 out of 57, because we are technically looking at this group here, that they like Coke and are male. And if we see this 12 here overlaps in this case. And it's always a probability out of the grand total. And then over the probability that they are a male. And this one's a bit easier here. And we're going to see that they are male is going to just be 29 out of the grand total of 57 in this case. All right. So if we clean these guys up, let's go ahead and try to review how we end up doing a fraction. A fraction technically means division. So I'm going to divide these two fractions. And if you recall, we never divide fractions. We turn them to multiplication. So we're going to do the reciprocal of the second one here. And then we're going to try to find some factors of 1 here, and we're going to clean this guy up a little bit. And so we end up with 12 out of 29, which is about 0.4130. And again, we're going up to 4 decimals in this case. I'm sorry, not 30, 38. Here we go. Okay. Now let's do this a little bit more intuitive. So probability they like Coke given that they are male. So here are the males. I'm giving you a hint that they are male. That means I only care about that row. I don't care about anything else since I'm giving you that hint. Now, think of that given symbol. You could think of it as division. It's really not, but we could think of it as division. And so in the denominator, I'm going to divide by the total males in this case here. So we're going to go ahead and put 29 males down there. Now, out of this row that we're looking at, so just what's highlighted here, we want those that prefer Coke. So out of this entire row here, we have 12 that prefer the Coke out of all of these here. And so that's going to give us 12 out of 29, which is approximately 0.4138. And I think this is the better way to think about this, is don't get too caught up on the formulas. We're going to just do it a little bit more intuitive. Okay, so let's try another problem here. So one more example. So why don't we find the probability a person is female given they like Pepsi. Okay. And you could go ahead and pause this if you want to go ahead and try this out. So here we go for this notation then. So probability that you're female given that you like Pepsi. And so again here, as we're looking at this 18 over 31, what we're going to look at is probability that the female is, that they're female given they like Pepsi. So right here is the given part. So that's my whole new kind of sample space there. I'm not going to look at anything else apart from that. So that's why that 33 is going in the denominator. Now from this group that I selected, how many of them are females? 18. So it's 18 out of 33. And so we could do it a bit intuitively without the actual formula there. And we're going to get to 4 decimals, about 5455 in this case here. Okay. Let's see how that relates to finding the probability a person prefers Pepsi given they are female. And so again here, it's kind of similar to this last one we did, but if you notice, I reversed the order here for these guys. And let's see how that plays out. And this one's going to give us 18 out of 28. Now again, the given here is that they're a female. So this time around, this is my whole new sample space there. I only have 28 total. And from this group that I circled, how many of them prefer Pepsi? It's going to be 18. So it's 18 out of the 28. And then we could do that to 4 decimals in this case here. All right. So I'll work out these other ones here. And you could pause it if you want to try to work them out before I go to the solution. But find a probability a person likes RC given they are male. And so here's our notation, probability of R given M. And that's going to be 29 in the denominator and then 2 up on above there. And again, because I'm giving you the hint that they are male, so I'm only looking at this group right here again. So there's my 29 in the denominator. And out of this group who like RC is going to be 2 of them. So 2 out of that 29 in that case. And then what about if we try the reverse of this one here, probability the female given they like Pepsi in this case. And I'll do this one just kind of using the formula in case you do like that, but I won't go into too much detail. So F and P is going to be, here is my F is going to be this group here, and P. So that and is going to be this middle region there, the 18. And then in the denominator that they like Pepsi in this case is going to be the 33 for those guys. And so that ends up giving us 18 out of 33 in this case here. Okay. and which is, did we write this guy? Let me go ahead and write this out then. 18 out of 33. I'll let you guys go ahead and type that into a decimal here. And this is going to end up being roughly 5455 or so. Okay. All right. And so let's move on and go into a little bit of definitions here of what we're going to call independent events. And so this is one event that does not affect the other event. So one event does not affect the other event. And an example of this might be a coin toss. So for example, if I flip a coin 10 times in a row and I get 10 heads, on the 11th try, am I more likely to get a heads or is a tails due now? And it's not. It's still going to be 50-50. Doesn't matter what happened before. I could get 10 heads in a row. On the 11th try, it's still going to be 50-50. And so that's why we talk about independence, something that doesn't affect what happened before. And you could think of this of the with replacement case. So with replacement. And then we could talk also about dependent events here. And so dependent events where we say one does affect the other. So dependent, one does affect the other. And an example of this could be if I pick 2 marbles from a pot. So if I select one, and we're thinking of it in the case of without replacement. So for example, if I got some blue and red marbles in a pot, and I end up picking a red one out, and then I don't put it back in, that one's done, and I'm going to go and select another marble. Now, the number of reds that are in there has changed, and then the overall has also changed. So dependent's going to be, think of it as a case of without replacement here. And something that's different now is that now we're going to be talking about multiple selections. So we're going to be having multiple events, but we're going to be talking about multiple selections there. So for multiple selections, we're going to use the multiplication rule. And so for independent events here, we're going to have P of A and P of A and B here, and that's going to equal P of A times P of B. Now, this is not the same P of A and B that we did with one single selection. That was 2 events on a single trial. Now what we're talking about is 2 events on 2 different selections, on 2 different trials here. So let me write the definition for dependent here, and then we'll get into some examples. So same thing here for multiple selections. Probability of A and event B happening is going to be probability of A times probability of B given that A already happened. Okay, and so it's still the multiplication rule, multiple selections. We're going to end up multiplying, but there's a slight difference here. And again, I don't want to get too caught up on the formulas. I'll write them down, but let's think of it a little bit more intuitive. So let me make up an example here. So say we have 2 red and 3 blue, and also let's put 4 green marbles in a pot. Now we're going to go ahead and shake these guys up here. And we are going to select 2 of these guys. Okay, so we're going to select 2 of these. And so let's find a probability that both marbles are blue. And let's do this with the case of with replacement. So we're going to do this with replacement. Okay. So probability that the first marble is blue, so I'm going to use that subscript of 1 right there in this case. So the first marble is blue. And we want the second marble to be blue. And again, I'm using that subscript to indicate the second draw that we're doing. So using our rule of with replacement, which is going to end up being the independent case here. This is probability of B times the probability of B2 here. So probability of B1 times the probability of B2 in this case here. So let's think about this first on the first selection. So the very first draw, I want to get a blue one. Well, how many blue marbles are there total here? Well, there's 3 blue marbles. But how many marbles are there total? Well, 2 plus 3 plus 4, which gives us 9. So when we go to write this out here, the first selection, we're going to end up with 3 out of 9. Did I say 2 before? No, yeah, I think I said, yeah, it should be 3 out of 9 in this case. Now, for the second selection, I'm going to get that marble and I'm going to throw it back in the bag and reshake it. So that's what I mean with replacement. It's like we're starting over. So when I go to select the second marble, I'm still going to have 3 out of 9 because all blue marbles were there. And the multiplication rule tells us is think of each selection independently or kind of by itself, and then we're just going to multiply these guys out. Now we're going to get 9 out of 81, which is about 0.1111. Okay. Let's go ahead and try the other case. Let's get 2 blue marbles here without replacement. So this time we're not going to go ahead and put it back. So probability that the first marble is blue and the second marble is blue, that's going to equal to the probability the first marble is blue times, we're using multiplication rule because multiple selections, that the second marble is blue given I already selected a blue marble on the first try. Okay, so let's try this again. Let's talk about just the first selection here. I still have 3 marbles out of the grand total of 9 in this case here. So we're going to have 3 out of 9. Now for the second selection, I already took one of these blue marbles out. So I now only have 2 blue marbles. And the total of 9, well, I took one of those out. So I only have 8 of them actually now. So my grand total is going to end up giving us 2 out of 8. So 2 blue marbles out of those. Because I have to consider what happened on the trial before. That's what we mean by dependent. And we're just going to multiply these guys out here. And we're going to end up with about 0.0833 in this case.